from the picture, how can we tell, or it's always this percentage?
What?
The percentage of the ripple
How can you tell the percentage?
from just the picture?
You can't. You have to be told. You have to be told what the voltage ripple is in these 5 cases. Okay, so the voltage ripple is the difference between the high voltage, the voltage peak, and the voltage minimum. Not the voltage zero, but the voltage minimum. Any questions about that? So now we've got a name for it, we've got some numbers for it, we've got a sentence telling us what it is, and why do we care? That's the next one. Why do we care about voltage ripple at all? Why are we interested or concerned about this?
Better quality radiographs.
Partly that, yes. The 2 issues that you're probably most fundamentally going to be dealing with the whole time. Quality radiographs and lower patient dose. The main 2 issues. That's why we care about it. Better quality and lower dose is obtained from which case?
The high frequency. Low.
Better quality and lower dose is obtained with less ripple. So less ripple is the ultimate goal. So is ripple a good thing or a bad thing? Bad thing. We want to reduce it as much as possible. Okay, so now we got why do we care? We know that's why we care. How does voltage ripple contribute to increased patient dose or poor quality radiographs? How does it do that?
More scattering radiation.
No.
That's how.
This is low energy photons, less scattered.
At this point, yes. Now is where you'd come in with that sentence about the lower energy photons. Voltage ripple produces more low energy photons. All right, that's enough of voltage ripple. Any leftover questions about voltage ripple? All right.
So if we were to describe how the effect of rectification on the X-ray, how can we explain that?
Effective rectification on the X-rays. It's an interesting one. What is rectification? Yes, so if we start off with the question, well, what is rectification? You're thinking of a voltage versus time graph, aren't you? You are now. first of all, what's the problem?
Longer exposure.
So what is the problem with that graph as far as producing X-rays?
Negative voltage.
Or,
I need a negative voltage, and I just need the rest of the sentence to go with that?
We need to flip it up or eliminate it
Why?
because we don't want low energy photons.
No.
Because of, okay, I don't know.
Problem is the negative voltage, but why is the negative voltage a problem?
Possible or
Pardon?
Is it possible?
Is it, no, I couldn't quite hear you.
Never mind.
What is the problem with negative voltage when we apply it? What are we doing with this voltage?
To produce X.
minimizing the flow.
Photons.
Where are we applying this voltage to?
Minimizing the flow of the electrons.
X-ray tube.
In particular, can you be more specific in the X-ray tube?
The filament.
No.
Oh, because it would repel electrons at half of the time, rather than just attract them.
So we're applying this voltage to the cathode anode system. And in order to get the X-rays, the anode must always be at a higher voltage than the cathode.
You mean on the other line than the cathode, right?
Hmm?
On the second line should be then the cathode. In order to produce
Make sure
X-rays.
the anode must be at a higher voltage than the cathode. Let's see. And in the negative part of the cycle, the anode would be at a lower voltage, which is why we will not produce electrons, and it'll essentially burn out the machine if you apply it to the cathode anode system. Okay. So if we, during the negative part of the cycle, we would be accelerating the electrons in the wrong direction. So that's why we don't want to do it. Excuse me. So that's why we're trying to say that we have to fix this. That's what we need to get rid of. Easiest way to get rid of it is to chop it off. We do that with the half-wave rectifier. The full-wave rectifier flips it over, and then we can play some games with some other types of engineering and smooth out even better. So did that answer your question about what rectification is and why we care about it? All right. We'll come back to that one. I'm gonna finish off this one. You saw this one last time. I just wanted to reprise it one more time. What's this graph talking about?
About, let's see,
Write a paragraph explaining what's in this graph.
space charge limited, or how like a certain, actually, I don't know how to explain.
Thank you for your honesty. It's much
I
appreciated.
think
Don't waste our time.
it.
If we were all only that honest. Nobody would be talking to anybody. So granted that it takes practice to take a look at this graph and write a paragraph to go with it.
Okay,
That's what you should actually try as far as homework or things like that. Try to write down a paragraph explaining everything that's in that graph. It's a real good exercise. And you had a question.
Yeah, the tube current is on the y-axis. The x-axis is the filament current. The kVp is a voltage in Y.
The vertical axis, that's always a good place to start, is the tube current. Meaning tube current, what do we mean by tube current? What do we mean? What is it? Where does this tube current exist?
It runs through the filaments.
Nope. We're just talking about this.
Cathode and anode.
It's the current of electrons that is flowing between the cathode to the anode. That is the tube current. So our tube current is on the vertical axis, and what's on our horizontal axis? Something labeled kVp. The VP ought to
It's the
ring a bell.
voltage
It's voltage, not only volts, it's kilovolts, right? kVp is kilovolts peak.
of the electrons. How many electrons are
Kilovolts peak. What are they talking about in these different kilovolts peak?
Volts in the anode.
Yeah, they're talking about something like this. We'll put the kV here. And I'll just do a full wave rectified for this example. That is kVp. And this is the voltage difference between the anode and cathode. And that max voltage difference is what's actually accelerating the electrons. Okay, so now we've got electrons and we have kVp. So we got a tube current, and we got some accelerating voltage. And then we have 3 different graphs for 3 different fill in the blank there for 3 different
Filament current.
filament currents, yes. So our tube current depends on the filament current, and our tube current depends on the kVp. And then the two remaining important parts of this graph.
Emission limited,
Yeah,
space charge limited, and
okay.
saturation point.
Start off with the emission limited. Notice that the emission limit is related to horizontal lines. Emission limited, horizontal lines, meaning, you must have meaning.
We can't accelerate the electrons in that region.
Nope, doesn't mean that.
No, but it's true what I said.
No, it's not
No?
true.
Well, then I don't understand, right?
Completely wrong, yes. You could not be more wrong about that.
And only a certain amount of electrons can,
Well, let's,
come off the filament.
Let's start, what is the meaning of a horizontal line?
It doesn't go.
They can't go any higher than
What is that it? They can't go any higher.
the amount of electrons being emitted. It cannot go any
Filament
higher than
current?
that.
The filament current does not change. Horizontal lines from your days in algebra making graphs. Come on, you can do it. Wake up. So that horizontal line there. In that emission limited region, the tube current does not depend on kVp. Or to say it the other way, the tube current only depends on filament current. To make a practical example out of it, if you're at 100 kVp and you want more tube current, cranking it up to 200 kVp is not going to get you there. Tube current becomes independent of the accelerating voltage. Okay, now that's based on it being the emission limited region. Think of it as you've used all the electrons that the filament has emitted. They're all been used, so can't do anything more than that. That's the meaning of the emission limited region. And then the harder one, well, I don't know if it's all that much harder, but I find it kind of an odd thing to think about, is that space charge limited region. What is happening in the space charge limited region?
have too much electrons, negative charge, then the electrons can't flow, like they block the flow of it.
There's a cloud of electrons, think space charge, that builds up around the filament, and that inhibits more electrons from being emitted. So the space charge inhibits emission, if you want to think about it in those kind of big terms. See, a paragraph might turn into a whole book. I'm sure there are books written on this stuff. Can I move off of this one, or is there any follow-up questions? We'll bring up the other one, which is this one. Another graph, which a paragraph is probably appropriate for. This one's got some strange things in it. First of all, notice it's got two different vertical axes. When one was bad enough, now we got two. One's full wave, one's half wave, and you know what they're referring to. Half wave rectified tube current and a full wave rectified tube current. And hence we have different numbers on the vertical axis. Horizontal axis, we've got the filament current. And one of the things to note right away is the huge difference in just the units. These are in amps, and these are in milliamps. So the tube current is tiny, but the filament current is big. Now, what is our filament current doing, and where does it exist?
It's on the cathode side.
The filament current is essentially on the cathode side, yes, but where does it exist on the cathode side? The name says it all. In the filament. So the filament, that's that little wire that runs in front of the cathode that's producing the electrons that are being accelerated. And we haven't even got to the photons yet. We're just getting the electrons accelerated here. All right, so we've got our two different rectified tube currents. We've got our filament current. And for something like 4.4 amp filament current, what are the possibilities indicated here? We have something there. We have something there. We have something there. And we have something there. What do we have? Let's just take this, let's take the lowest point here. Read it off. What does that number correspond to on that side?
130, 40.
I would call it 120.
Milliamps.
So if we call that 120, 120 what?
Milliamps.
Amps, half full wave.
Yeah.
And notice that would be about half of that in the half wave rectified. Why does it go down by half? In the half wave?
Because we eliminate the negative.
Because what?
We eliminate the negative charges.
Why is the half wave half of the full wave?
Because it's half the full wave.
Because it's half a full wave, yes. Because it takes twice as long, because we have these gaps where nothing happens. Those gaps are important. Okay, back to this. All right. So we got 120 milliamps of tube current at what kVp? So you read all the way up. It's a 50 kVp line.
Sorry, can you repeat the last part? We have 120 milliamps half current,
Full wave
full
tube
wave,
current
okay.
at 50 kVp.
Oh, okay.
And 60 half wave.
And 60 half wave. Okay, see if we can get this out of the graph. Looking at this graph only, if I increase the kVp, will tube current increase?
You mean both currents, the half wave and full wave?
Ratio.
Just look at the full wave side. Will the full wave tube current increase if I increase the kVp?
Not necessarily.
So the point, I guess the options are yes, no, or not necessarily. Or none of the above.
Yes.
All right, well, let's crank up the kVp. Let's go up to 100 kVp. Same filament current. What's my full wave tube current now? About 160, 170. Did the tube current increase with kVp?
Yes.
Yes.
Yeah.
But it's confusing because we just said the tube current, kVp doesn't affect the tube current.
That was in the previous graph.
As a theory, because the filament current is affected by the
So-
tube current or vice versa, like,
If by increasing the kVp, can you tell, and seeing what happens to the tube current, can you tell whether that is in the emission limited or the space charge region?
Space charge.
Space charge, yeah, let's go take a look at that. So we got the 4.4 current. Space charge graph, okay, this 4.4 is below the 4.6. And we're kind of down in this region, going probably sort of right into it. Not too sure that these graphs are completely in agreement with each other, but they're pretty close. Notice as you go up to the different kVps, they get closer and closer together, indicating that there's going to be less and less change as the kVp gets higher and higher. This only goes from 50 to 125. So on this graph, that's in this region, probably in here. I don't think that line flattens out quite as much as Bouchon is indicating, but it's his textbook. All right. Got everything I wanted out of there.
so, I'm a little bit confused. I would like to clear this.
How could this be confusing? This is clear.
No, when we relate the kVp to the current of the tube. So it does affect it at a certain region, right? And after a certain region, it doesn't affect it anymore. In other words, right?
what calculus is for. It's because I hate this sentence. Note the increase of the tube current with the KVP decreases. That ought to really confuse you. The increase decreases. Smaller rate of change.
Okay.
Yes,
I have a question.
go.
So what you were talking about, the emission limited and the space charge limited on this graph? How do you tell?
Higher up is, well, basically higher, where the KVP lines get closer and closer together,
Yes.
that's where you're in the emission region.
Okay.
And then there's very little change in the tube current after that. So if I were to guess where, say, the 150 KVP line would be, I'll speculate. 150 KVP line is probably going to be just like right there. And probably the 200 KVP line is going to be something like that. So what we're trying to indicate is these KVP lines get very close together, indicating that there's just no dependence of the tube current on the KVP at higher KVPs, which is why they didn't draw in the higher KVP lines.
So does that mean the space limited is not on this graph?
The space charge limited would be where the KVP lines are farther apart. So that's what you're looking for. Far apart, space charge. Close together, emission limited. And now for some good news. You ready for some good news? I'm just gonna write down the page number here. That's not the good news. Page number 9. The good news is that this graph and its cousin, the other one, are the only two things I'm interested in chapter 6.
Yay.
So that and the other one is the only thing from chapter 6 that you need. I mean, there's a lot more good stuff in chapter 6. But I'm interested in you understanding that part. All right. Now I want to go back to this picture. So we're kind of back in chapter 5 a little bit. I want to finish off a few things from chapter 5. Okay, so you've had 30 seconds to look at that. Same picture and no labels. Okay, so, but let's just see what we can do before we see labels. Okay, we see what this thing is. That's our what? X-rays. And these X-rays are coming off of the tungsten rotating anode. Yeah. This is our cathode. So that's our cathode, there's our anode.
These are the photons then that are coming from
These
our
are the photons, yes, the X-ray photons. All right, so this is the rotating cathode, or anode rather. It's rotating. Notice that this is completely isolated from everything else on the planet. It is not attached to anything. And how do we make this thing rotate if no wires go to it?
Magnetic fields?
Magnetic fields, yes, induced electromagnetic fields. This is able to rotate by way of induction. The use is an induction motor, which is kind of like another variation on a transformer, really. By having one changing magnetic field someplace, you can get something else going on. We're not going to worry about how induction motors work, but you should be aware that this is a important use of an induction motor and important use of induction in the X-ray tube. All right. The next thing we're interested in is this little thing here that's sort of at the, well, that is at the cathode. What's right in front of the cathode?
Filament.
The filament. And what does the filament do for us?
Produces
Electrons.
Gives us electrons. So the electrons are coming off of here and they're being accelerated across that gap. So far, so good? Okay, if this is the filament, we follow the line back. This is a wire. What is the filament attached to? A transformer. So what kind of transformer does that look like to you? Looks like a step-down transformer. And that's right, our step-down transformer delivers a large filament current. Step-down means lower voltage, higher current. Well, if that's a step-down current, what's the one right, a transformer, what's the one above it?
Step up.
And what do we need that step-up transformer for? Voltage in a very complex way, going on this side to the cathode, anode, and on this side in some complex way to the cathode. So there's our transformer. This is another part of a transformer here. And what do these little things look like? This thing and these various little knobs, buttons, things. What might they represent to you? Well, it's something that's pointing there, but maybe you could point over there or down there, point up there. This one's similar. What do you think that's doing? Magnetic fields. Good answer to almost anything in this chapter, yes. When in doubt, magnetic fields. Yes, it's actually tapping into different parts of the transformer. So it is selecting different parts related to that magnetic field. That's a selector switch. So this thing is not quite as bad as you thought it was, right? Let's see, let's go back to the labeled ones now that we took all the fun out of it. So you see you've got our KV selector switch, some other weird stuff related to time selection, filament transformer, transformer oil, cathode, the stator windings for the induction motor, the anode or the rotor motor, all these kind of good things. It's not such a scary diagram, is it? Yeah, that's not bad. All right, with that in mind, we'll put that away. And what is everything that I'm interested in chapter 5? That picture is one of. Chapter 5 is all about the rectifier and the voltage ripple and this tube circuit. So that's what I'm interested in chapter 5. A little bit more than in chapter 6, but still not too bad. Because with that, I would now like to move over to chapter 7.
We're done with chapter 6.
Mm-hmm. There's a lot more in chapter 6. I don't mean to give a short shrift, but I'd rather get on to chapter 7. Because chapter 7 gets more fun. X-ray production. Well, it's more fun from my point of view. So now we actually want to finally produce X-rays. And how are X-rays produced? So far we know what we're producing. We're using accelerated electrons crashing into an anode to produce X-rays. There's 2 A's in X-ray, right? So we have our accelerated electrons, they hit the anode in that process, X-rays are produced, as well as a whole bunch of heat. So the X-rays are a good thing, the heat's a bad thing. That's why we need a rotating anode to help cool it off. So we have some kVp between the cathode and anode. The electron is screaming towards the anode, and it collides with the anode. Now, what is the anode really? It is rotating, but it's... Any guesses as to what the anode really is?
Tungsten.
It's a chunk of metal. Yeah. And what is a chunk of metal?
Tungsten.
Tungsten, yes, we got it, it's tungsten, it is. But what is tungsten? Basic theory of matter.
Solid?
Solid.
A solid. A bunch of atoms, yes. So our electron is actually headed for a bunch of tungsten atoms. And I don't really want to draw all those atoms because I'm only interested in one, really. The one that it's almost going to hit. And so we'll focus on just one atom here. And of course these drawings are not to scale in any sense. But I tried to indicate something and something else around it. What is the graphics meant to convey? Electron shells around the tungsten target atom. What's in the electron shells? Electrons, yes. All right. Do electrons attract or repel each other?
Electrons repel each other.
Right. Electrons repel each other. And so initially, this electron screaming towards it really just sees a bunch of electrons, which says it would really want to go the other direction. Does it? It's not attracted to it. So the electron starts to deviate around it because of the electron repulsion. However, so that's one possibility of the path. However, there are other possibilities. In particular, one that might, I'm going to blow it up a little bit, look like this. And we might imagine that this electron is able to get, let's see, I need to draw it a little bit differently. How do we imagine that this electron, for some reason, is able to get inside some of the electron shells. Maybe it was just fast enough, or it's just the right place at just the right time. It actually gets inside some of the electron shells. And now, yes, it does see these electrons around it, but it also sees a very large, positively charged nucleus. And how do opposites, do they attract or repel each other?
They attract each other.
They attract. And so in this case, the electron might do something like that. So in this case, it's actually turning towards the atom if it gets inside the shells and is attracted to the nucleus. In the top case, it's actually sort of being pushed away from the electron shells. The important thing, you don't care about all of that. What you care about is that its path has been changed. And that's how we produce photons. When we refer to a change in the path of the electron, we really mean the electron has been accelerated. And this is by the target atom. And when electrons are accelerated like this, they produce a photon. And that's the photon that we are most interested in. Okay, so go back about 200 years in time. We have a beam of electrons, and we have an electron detector. And it wouldn't be too surprising to you that if I aim my beam of electrons at the electron detector says, yes, you got electrons there. They're coming at me. I'm registering them. Okay, what happens when we put a piece of metal foil in front of the electron detector?
It's not gonna, it's gonna, the voice of blocking electrons?
Yeah, it blocks some of the electrons. Some electrons still get, a few still get through. But most don't. So if most of the electrons don't reach the detector, we say the electrons have been stopped, which is really the wrong thing because they haven't been stopped, they've just been deflected. Spending a little bit of time on that because the word for this, and it's in German, any German speakers in here? Before I've used this word. Brimstrawling? Brimstrawling means breaking or stopping. And this is it's called Brimstrawling Radiation. And that's due to the stopping of the electrons, even though by stopping we know they're not really stopped. They're really deflected. So in place of stopping, we should use deflected. That would be a better word. I don't know what what deflected is in German. But anyway, they're not going to change this word now. It's been used successfully for the last 150 years. They're not going to change it. So we're stuck with the term Brimstrawling radiation. And this is the source of our X-ray photons. And so our next thing to do is to make a histogram of our X-ray photons. Number and energy. So if you want to make a note to yourself, at this point we're leaving the electrons behind. The electrons have interacted with the target and they've been deflected, and in the process of the electrons being deflected, the photons are created. And now the photons, we study the photons, and they produce something like this. Something that has a definite endpoint. Usually there's kind of a peak, something like that. This is an important point, the highest energy photon produced, also known as minimum wavelength. Why is that an interesting point? How is it related to anything else we've been talking about?
Because the wavelength affects the energy of the
Forget the word minimum wavelength, just think about highest photon energy.
With the first energy, the wavelength is.
Yeah. What does the highest energy photon have to do with anything that we've ever talked about? Pardon? The ripple, you could get there from that, and it's not the most direct way I wanted to get there.
The peak?
The peak. This highest energy photon is related to the peak voltage. So the energy of the highest energy photon is related to the kVp voltage of the cathode anode system. Now, how are they related? Max photon energy is just E times kVp, or as it's most commonly written, KeVp. So that E stands for the electron charge, the kVp is the voltage of the cathode anode system. Which means this is what? This is the electron kinetic energy. So that is the electron kinetic energy, and what we're really saying is that once in a while, all of that electron kinetic energy is produced as a single photon, but it doesn't happen very often. So hang on to that thought that it doesn't happen very often. And we're trying to connect that idea with the fact that the number of photons gets very small as we get towards the tail here, and then it dies after that. It cannot, nothing can show up after that, right? Because you can't produce more energy than the electron had to start with. All right. Total area under the curve. Anyone take calculus in here? Oh, good. Not that we have to calculate it, but that's what calculus is all about, is calculating this stuff. We're calculating this area under the curve. Well, we're not going to calculate it, but we're interested in it. Total area is the total number of photons produced. So we kind of like to be able to recognize sort of the landmarks of these histograms. And something with more area has more photons than something with less area. All right, throw a lot of information at you today. I'm not going to throw too much more at you. You see the point where there's the maximum energy. According to this graph, where is the minimum energy?
The peak up here?
Minimum.
Oh, the minimum energy?
Yeah. According to the graph. If this was the highest energy, you go to the other end. Lowest energy is 0. Yes. Wasn't trying to trick you there. The harder one. And this one is a subjective answer. Everybody will pick it slightly differently. You'd kind of like to know what the average energy is. Look at that graph and try to tell me how you would identify the average energy.
If we look at the x-axis, it would be 0.
Okay, so now, did anyone take statistics?
Yes.
All right, there are. Statistics is a really good class to take, by the way. I highly recommend it. It's very one of the more. I took it late in life, but it ended up being one of the most useful classes I ever took. And then I taught it for a whole bunch of years.
The highest minus the lowest divided by 2,
The highest and the lowest divided by 2.
like average? No.
That would give you an average. So there's basically 3 types of averages, and you just described one average. What highest and what lowest are you looking at on this graph?
The highest energy photon.
Okay, which is out here. And the lowest energy photon?
In the beginning.
In the beginning.
Okay.
And so something plus 0 is just something, right?
Divided by.
And divided by 2, and that's one average.
Yeah.
And that would be about here.
But then how,
Right here.
yeah,
So,
how would you
constant.
And you also want to get the total area.
The size.
how would you, how would you get the whole area?
Well, this is one sense of getting sort of an average energy. And it would work really nice if that distribution was symmetric,
Yeah.
but it's not symmetric, and so there's a problem. And so in statistics, there's 3 ways of calculating an average, and you decide which one is the most useful for you, depending on what you're doing. The other one that comes up in statistics a lot is just if you find the peak. And this has the name of, in statistics, the mode. Mean, median, and mode. And then there's another one which is known as the median. And the median is probably the one we'll try to aim for most often here. The median means that this is half the number of photons. And you don't have to worry about all these names for average. What I'm really wanting you to see is that they're all pretty close to somewhere in the middle. And whichever way you like thinking about it, half the photons are down here, half the photons are up there, or that's where the peak is, will usually work, but not always. So the mode is probably the least useful to us. Or you just look at the highest and lowest, divide by 2, and there's your average. We need to have some way of considering where the average energy photon is. It's kind of a strange idea. There's the highest energy photon, lowest energy photon, and there's a photon with the average energy. And many times when we're talking about these distributions, we want to talk about what happens to the average energy photon. That's a great place to stop. All right, 3 chapters, 1 day.
Scroll down a little bit. Yeah.
Fortunately, we just did highlights from 5 and 6.